Okay, so in this video, we're going to look at more series and maybe a little bit more complex series where we can't necessarily use a geometric series kind of definition to know that the interval of convergence is going to be as an absolute value less than 1 and solve for that. So here's an example where I've got it's definitely a power series. I see x to certain power. It's alternating, and the denominator is a factorial. So it's definitely not geometric. So what I'm going to use next is actually the ratio test, because I know that the ratio test that's kind of similar, I think, in a way to the geometric series test, where we want to compare it and make sure that it's the ratio of any two consecutive terms is less than 1. And as long as that happens, we know that we will converge. So we want to find what values of x, when will this thing converge? So just to be a little bit careful with the notation. So I'm going to have the limit as n goes to infinity. And so then that's absolute value of -1 to the n plus 1. And then it's x, and be really careful because it's one more. So think about this for a second. So it's one more. So it's 2 quantity n plus 1 plus 1, right? So that's like 2n plus 2 plus 1. So that's 2n plus 3. Just to be careful of that. That's 2n plus 3. And then same thing down here. It's 2 times n plus 1 factorial, right? So that's 2n plus 3 factorial. So be careful about that. So over 2n plus 3 factorial, and then divide by the nth term, which is -1 to the n, and then just x to the 2n plus 1 over 2n plus 1 factorial. And so again, just wanted to make sure, take a little bit more time to make sure we see that what is the next term. And the reason that's like in 2n plus 3, if you haven't recognized that these are odd powers that we have for x. So the next odd power would have to add 2 more in theory. So like plus 3. Okay. So then when we do the reciprocal and the alternating part will, cancel. So then, there we go. So then that equals the limit as n goes to infinity. And what I'm going to do, so I guess I'll just rewrite this. So it's x to the 2n, and then I can think of it as like x cubed if I want. So like x to the 2n times x cubed, because that would have been plus 3, and that this is 2n plus 3 factorial. And then when this thing flips around, it's going to be 2n plus 1 factorial, and then that's x to the 2n, and then that'll be just times an x. So again, that was kind of nice, because now I can see that those x to the 2n's are going to cancel. And this 1x will cancel with one of those, so we'll get x squared. Now, 2n plus 3 factorial, I guess I could have expanded that one as well, but that one is going to be, so this limit as n goes to infinity. So I still have my x squared up here, and then this is 2n plus 1 factorial. But down here, that's 2n plus 3. And then if I think about, okay, well, what's 1 less than that? Well, that's 2n plus 2. And 1 less than that is 2n plus 1. And then there's the part of the factorial that'll now cancel with this, which is nice. So if I take a look, what do I have? I have the limit as n goes to infinity of x squared divided by 2n plus 3 times 2n plus 2. And the thing is, the only part that has an n is the denominator. So that limit is going to go to 0. And since I used the ratio test, I know that as long as I'm less than 1, which 0 clearly is less than 1, then I know that this is going to converge. So it doesn't really matter what value of x. This is going to converge for all x. And the reason it's going to converge for all x is because my denominator gets big so fast that it doesn't really matter what value of x I put up there. So since it did say find the radius of convergence, since this converges for all x, my radius is infinity. So since our series converges for all x, the radius is equal to infinity. So if it looked for an interval, then I could say from negative infinity to positive infinity. And since it's the whole interval, I don't need to have any, right? I don't need to have any endpoint checks because you can't ever get to infinity. Okay. And so I know that it only asks for radius, and now example 4 is going to say, okay, let's find interval. So now I want more than just the radius. I want to know the endpoints. So I put a little reminder, like check the endpoints. But we've been checking the endpoints, right? Okay, so here's another power series. And so for this power series, x to the n over n. So I think maybe what I will do is I can think about it as I guess I can think about it as a geometric sequence, since I have no factorials or anything else, or I could think of it as a ratio test. So I like ratio tests, so let's maybe do that. So limit as n goes to infinity of x to the n plus 1 over n plus 1, then divide by x to the n over n. And I'm choosing the ratio test because as long as that's less than 1, I'm guaranteed convergence. So I just like to practice that one. You can see the geometric series would have worked as well. So x to the n plus 1, that's x to the n times x to the first over n plus 1. And then when you do the reciprocal, you have n over x to the n. So x to the n will cancel, and we now get the limit as n goes off to infinity of x times n over n plus 1. So that limit, since n is going to infinity, I kind of just am focusing on the things that have n, right? Which is basically, it's a 1-to-1 ratio. So this is going to equal 1 times x, which is just x, because the n component just goes to 1. So I get x. And so this will converge as long as that's less than as 1. And so we can think about it as a radius. So as long as that value in absolute value is less than 1, will converge. Well, in terms of a radius, it's centered at 0, and it's a radius of 1. Now, in terms of an interval, the bare minimum is this, right? So we know, again, if thinking on a number line, if we're at 0, we can go 1 to the right and 1 to the left. So we have an interval of convergence of at least from -1 to 1. But now I gotta check the endpoint, right? So let's check that endpoint. Let's check what happens when x is equal to 1. So the series when x is 1 becomes n equals 1 to infinity of 1 to the n, which is just 1 over n. Well, we know this diverges by p series. So that endpoint doesn't help at all in terms of increasing one more value to our interval of convergence. Diverges by p series. It's also the harmonic series, right? Now, what happens if x is -1? The series now becomes -1 to the n over n. Now, the alternating series that is 1 over n, that will converge because it's alternating, right? So for that one, I can say that converges by the alternating series test. Now, if I'm going to use alternating series test, I should probably make sure that I just real quickly address the two conditions. I know that the sequence 1 over n is decreasing. And then I also know that the limit as n goes to infinity of 1 over n equals 0. So I've just basically proved that series converges. So my final answer then, the interval of convergence, means I can now include -1, but I still am going to exclude +1. So that, and then in terms of an inequality, it would look something like this. -1 is less than or equal to x, which is less than 1. Okay. Now, so let's look at the next example. And then, so for the next example, if you wanted to make this like a geometric series, you could think about that, right? It's a power, right? So, like if I rewrite this, I know it's alternating, so that's not a problem. But like I could think about it as x plus 1 over 2 to the n, right? That series. And so, I mean, I could use the ratio test I used in the last example. Maybe this example, I'm going to use just my knowledge of a geometric series. So as long as my ratio in absolute value is less than 1, then I know it'll converge and I can check the endpoints. So the alternating part doesn't really bother me too much. It's just this quantity x plus 1 over 2, since that's what I'm raising to the nth power, I have to just make sure that that's less than 1. Okay. I can open this up. So it becomes -1 is less than x plus 1 over 2 is less than 1. Multiply 2 to both sides. And so right now I'm noticing that my radius, I'm centered at -1, and my radius in this case is going to be 2, right? Because I'm equaling, I could have put that into absolute value, made it equal 2, but let's go ahead and actually find the interval. So we're going to subtract 1. So it becomes -3, subtract 1 is less than x, which is less than 1. So again, it's centered at -1 with a radius of 2. So from a graphing point of view, if I said, okay, here's -1, oops. So here's -1, a radius of 2 means going 2 in this direction, I would be up to 1, and going 2 in this direction, I'd be down to -3, which is what I have at inequality. So I at least know it's between -3 and 1. So now I need to check the endpoints. What happens when x is -3? Okay, so, well, when x is -3, then I get -3 plus 1, which is -2. So I get -2 to the n. So I get -1 to the n, and then -2 to the n, all over 2 to the n. Well, if I want to simplify that, since -2 to the n could be thought of as, it's -1 times 2. So in other words, I have a -1 to the n and a 2 to the n. Like I'm just breaking up that negative over this 2 to the n, and those cancel, and -1 to the n, -1 to the n, those are just 1. And so what I end up getting is the series as n goes from 1 to infinity of a bunch of 1s, right? So that doesn't work, right? If I'm adding 1 plus 1 plus 1, that's not going to give you a sum that's infinity. So it's definitely not, it's not -3. So this series diverges. Okay, because, well, you diverges by the nth term test, right? Limit does not go to 0 by nth term test. Okay, so then let's check when x is equal to +1. So when x is +1, now my series is, let's see, n equals 1 to infinity. So that's -1 to the n. When x is 1, that's 1. 1 plus 1 is 2 to the n over 2 to the n. So now, the 2 to the n's cancel a little bit cleaner. And so we get the series n equals 1 to infinity of -1 to the n. So this alternates 1, -1, 1, -1, 1, -1, 1, -1. Guess what? That still diverges, right, by nth term test. So in this case, neither endpoint worked. Diverges by nth term test. So the only x's that work for this particular series would be between -3 and 1. So either you represent it like this, most likely though you'd see it like that. And again, let's think big picture. What does that tell us? That tells us you could pick any x in this interval and put it into that particular series, right there. Right. So what if x is, like 1/2? Because 1/2 falls within that interval. So if you chose x to be 1/2, and you said 1/2 plus 1, which is 3/2. Oops, didn't want to go highlighter. Sorry. So if I had chosen x equals 1/2, so 1/2 plus 1, that's 3/2. So if I said, okay, 3/2 to the n over 2 to the n, and make it alternate, -1 to the n, that series will converge. And it'll converge for every particular x that's within that interval. So that, again, that's what it means when it says like find the interval of convergence, right? Because what you're doing is you're trying to, basically you're solving an equation, find all x's such that your series will converge. Yeah, like the two main tests that are going to help us would be a geometric series test, if you recognize it just powers, or a ratio test. So, okay, so I'm going to actually pause this video and then do the last couple of examples on a third video.